Hello, everyone. This will be a little bit different from what you've been listening to today. When David asked me if I wanted to do a talk, I said, well, I could do something on something a little different than what you normally hear about, but not actually too different. So what I'm going to do is talk about what I call a multi-wavelength, extremely high frequency imaging solar radio telescope, or how I learned to love my spectroheliograph. So first we'll start with a brief review of the nature of light. And of course, this should hopefully be a very, very brief and elementary approach. So light can be a particle or a wave. Radio can also be included in the electromagnetic phenomena. And the distinction between light and radio is based on wavelength, frequency, and how it's detected. In other words, radio waves and light are the same thing. And of course, here we have the electromagnetic spectrum that you're all familiar with. And we can see that we're going to talk a little bit about what's right here in terms of the visible portion of all this. We've heard talks today that go way out into the X-ray and gamma ray region and down toward the microwave region. So light can be a particle or a wave. On the left side, we see depictions of photons, which occur because of transitions within the atomic structure, and a wave phenomena usually depicted by a sinusoidal wave having a wavelength and moving in a particular direction. However, depending on how you want to detect it will depend upon whether you have a wave or a particle phenomena. If it's a particle of light that you want to deal with, we call that a photon, but photon can be used for any particle of the electromagnetic spectrum. And in this case, we could use a solar cell, which depicts light as a particle using the photoelectric effect, thanks to Einstein. And then if you want to detect light in terms of its wave property, you can set up oscillations in a conductive medium, for example, an antenna. So the distinction between light and radio is based on wavelength. On the left, you see, I actually use this as a 1.4 gigahertz radio telescope. So I'm not that far removed from what's going on here. And this also is a radio telescope if you look at really high frequency. So the spectrum. Typically, we could take what we normally call white light, which we see, send it through a prism, which is a device that can disperse that light into its component wavelengths, and you have a rainbow or a spectrum. An interesting thing about light when it's interacting with matter, and we start with a heat source, you'll get a continuous spectrum from blue to red without any breaks between the colors. They sort of just blend. If you put an intervening cloud of gas in the way, you'll get what's known as a dark line or an absorption spectrum. And because the energy that goes into this cloud can't stay there, or else the cloud keeps heating up, it's going to get rid of that. And if you look off at some angle, you'll see a bright line spectrum. So a solid, liquid, or high pressure gas, when excited, will produce a continuous spectrum. A cool, low pressure gas, when excited, will produce an absorption spectrum. And a hot, low pressure gas, when excited, will produce an emission spectrum. And these properties, known as Kirchhoff's laws, apply to all electromagnetic radiation. Again, depending on how you're detecting this signal that you're interested in will depend on what your equipment's going to look like. Here's an example of an absorption of dark line spectrum. And we're going to be talking about this particular line, which is the hydrogen alpha line. In 1802, Wollaston noticed that the visible spectrum from the sun had several dark lines in it. Fraunhofer was the first person to build a spectrometer using a narrow slit and a small telescope. Now, Isaac Newton actually was on to this a lot sooner than Fraunhofer, where he used a circular prism, a piece of glass, put a hole in the curtain in his room, and had a beam of light going through the glass and produced a spectrum. What Fraunhofer did was, by sending the light through a narrow slit, he was able to essentially see that the spectrum was made up of lines. Those lines are actually the images of the slit. This is a complete solar spectrum, all the way from infrared to ultraviolet. So let's take a look at the sun, and this will be our point of focus today. And in this little cartoon, we can see all the major regions of the sun. The photosphere of the sun is what we normally think of as the surface. Of course, there's no surface there, but it's what we see when we look at the sun through the proper filtration systems. Put very welder's glasses or what have you. I wouldn't recommend that, but there are white light filters that you can use to look at the sun. And on the surface, the photosphere, you will see sunspots and granules. And in these regions, there's a great deal of activity going on, typically in the form of magnetic energy. If we move up a little bit, up toward a surface above the photosphere, then we come to the chromosphere. And this is where you see the typical flares, the tongues of fire that jump off that you see in those wonderful videos depicting what's going on the sun. And here we have a flare and prominences. And if we go out further, we have the corona. And what's interesting is, as you move further out from the surface or the photosphere of the sun, the temperature goes up. And you would say, well, wait, that doesn't make much sense, because if the corona is very hot, 2 million degrees or so, compared to the photosphere, which is about 6,000, how does that make any sense? Well, again, we look at the definition of temperature, which is the average kinetic energy of the particles that happen to be moving around under the influence of some force. If we move into the center of the sun, then we have a convective zone which produces the granulations that you see on the surface, and a radiative zone where the ultimate energy from the core is transferred to the radiative zone. The convective zone here, if you think of this layer boundary between the two, would be like the your oven, the burner on your oven, and the convective zone could be thought of as pudding within a pot, that as the heat is implied or impressed into this region, the pot starts to cause the pudding to bubble like that way, and that's where you get the these granulations. This is an image, a white light image that I took with the device that I'm going to explain today, of the photosphere on the 5th of February this year. And here you can see sunspots, which you normally would expect to see on the photosphere. And if you look closely, you might see some sort of fuzziness there, which are the granulations that I just talked about. And why this date is important is you'll see as we go along. And here is an image of the chromosphere, which is taken just above the photosphere. And you can see in the region of some of these sunspots, these very energetic areas, which are depicted here by bright areas. And we can see some other features, filaments, and the sun is going to be rotating this way. And of course, you can also see prominences coming off the sun. And again, this is the same date, the same image taken at the same time. The active region, which caused the large flare and coronal mass ejection during the last week of January, the first week of February, is here. And this is the one that caused such interesting problems, I guess, for Elon Musk. So let's take a brief chat into what is a radio. And of course, all the hams in the audience immediately can recognize this as a radio. But what's interesting is if a ham was talking about how this radio tunes, the ham would say it tunes from 160 to 60 meters. A physicist would say it tunes from 30 kilohertz to 56 megahertz, and an astronomer would say it goes from 6 to 160 meters. And you say, well, that's just like the ham, but the astronomer puts the blue end, the shorter wavelengths, to the left, and moving outward to the longer wavelengths. That's just the distinction. And then, of course, the physicist is going to talk about frequency. So this is also a radio, and I can actually, this is it. This is the device that we're going to be talking about today. And it is also a radio. And it tunes, if you're a ham, from 7,200 to 390 nanometers. If you're a physicist, 3.8 times 10 to the 14th to 7.7 times 10 to the 14th hertz. And if you're an astronomer, 390 to 720 nanometers. So if we look at a basic radio receiver, you have an antenna, and of course this is very basic, but you have an antenna, tuned circuit, and a detector. And schematically might look something like this. Well, if you have a basic spectroheliograph, you also have an antenna, which we normally use as a telescope, and it has a tuned circuit, which is a grating, and it has some sort of a detector. In the case of this instrument that I built, a CMOS. And so you see the telescope here, the grating here, and the detector here. And here we have a slit. Image is collected, goes through a couple of a lens here, the diffraction grating, a second lens, and onto the detector. In this particular device, a reflection grating is used. So the incident light will come in, and the grating is made up of a series of literally scratches on some sort of substrate. And the incident light will be diffracted according to the scratches and how the mechanics of those scratches are actually built. So let's take a brief history of the spectroheliograph. It was developed independently by George Hale and Henri Alexandre Deslatre in the 1890s. This is Hale's design of a spectroheliograph. And he was doing this in terms of one of his master's thesis. And he was interested in designing something that would allow him to look directly at the sun in specific wavelengths. And so what was done is you'd have a slit. Here comes the light coming in, a lens, a mirror that would take this columnating lens would take the beam of light, send it through two prisms, and then through another lens, which then would form, this would be the focal plane. But what he did was he put a moving photographic plate in this region, and very cleverly figured out a way of moving that plate so that he could just scan. This second prism would actually select the frequency at which he was going to collect this image. And here you would see, if you were looking, if you had an eyepiece there, this would be the slit, this would be the sun. And as you move the plate and also cause the telescope to move, this would then form an image. You'd build an image of. He did most of his work at Kenwood Observatory, which was his private observatory built by his father in the Kenwood section of Chicago in the 1890s. This is what his observatory looked like. This is his spectroheliograph on the 12-inch refractor, which was here. And there's Hale in the laboratory. Ultimately, he ended up on Mount Wilson and built the Solar Observatory, which was used to do this work. And these are typical images that were captured in 1915 of an area, an active region on the sun in hydrogen alpha light. Again, looking at the emission off of the sun at a very narrow frequency or wavelength or bandwidth, however you wish to to deal with that. Now, this type of device, a spectroheliograph, as the name implies, allows you to take a picture, an image that you can actually look at from a photograph. But Hale wanted to go one step further and develop a device that you could look through directly at the sun at the appropriate frequency you were interested in. So he proposed the spectrohelioscope, and here's a drawing made by Russell Porter. Here at the front end, you would have a coelostat, which is constantly monitoring the sun's position and sending the light directly to several other mirrors back to this area where you would sit, and there would be a series of moving slits that would go back and forth, and when you synchronize them, you would actually see an image much like the frames of a motion picture going back and forth. Once it's in sync, you would do this, and you can tune the wavelength, or you can tune the device to look at various frequencies. Now, most of the stuff that comes off the sun, because the sun is mostly hydrogen, the H alpha line is the one that people look at to see what the chromosphere is doing. But you can also look at the calcium line. You can look at the iron line. You can look at, if you don't pick the right line, you'll end up seeing a white image, a white light image. To give you an idea of size, this was the Henri's device in France at the Observatory in Paris, and quite large. These were images from his observatory in 1910, from the Meudon Observatory, calcium light on the left and hydrogen alpha on the right. This was a spectroheliograph mounted at the Yerkes Observatory, the 40-inch telescope, by Hale. This was one of Hale's instruments, and for scale, you could see the individual setting this up and getting ready to photograph an image of the sun, probably in hydrogen alpha. And at Kitt Peak, we have the McMath Pierce Solar Telescope. McMath was interested in not only solar physics, but he wanted to build a device that would allow you to take real-time images of the sun. This telescope is no longer online, so to speak, but it's being taken over by the visitor center at Kitt Peak. And actually, amateur astronomers are actually responsible for keeping this thing going now. There was an NSF proposal and was funded in 2018, and this will still be used for research, but you can put in a proposal and use this telescope. It's just, and it's amazing. It produces a 1 meter wide diameter image of the sun on a special table. You can do all sorts of wonderful things with this. This is my device, which is ready to collect data. And what you see here is the spectroheliograph. Now compare this in size to the one that you just saw earlier from Hale's device, or the French astrophysicist. And what I have here is this end connects to a telescope. Where am I? Yeah, there we go. This end connects to a telescope, as you see in the diagram, and light goes through here. Here's the tuner, okay, and the detector, and the antenna is the telescope, right? So now what happens is this then will, what I had to do is stop this down. The sun is very bright, and we were just talking earlier about paint on a reflective surface and how you can generate an awful lot of heat if you're coming to a focus. Well, this is the same problem. However, it's not a problem because I'm looking at a very small amount of energy once it gets through the grating to the detector. But what I did was I stopped down a 60 millimeter telescope, which is this device, to 25 millimeters. So the images that you're seeing from this device are taken with essentially a 25 millimeter, 1 inch diameter aperture. So now, what are some of the effects of geomagnetic storms on the Earth, which we can detect when we look at the chromosphere of the sun? We can see the activity that's going on. We can see flares erupting, and things happen. So one of the first things that you normally associate with these geomagnetic storms, which are major disturbances in the magnetosphere of the Earth, is the aurora. And not every flare will produce a coronal mass ejection, which is the actual material that gets to the Earth that interacts with the Earth's magnetic field. So geomagnetic storms can cause all sorts of havoc with our electrical systems. They can induce currents, saturate magnetic cores within transformers, and cause voltage and currents traveling along conductors. Geomagnetic storms produce large short-term increases in upper atmospheric temperatures and density. And this is interesting if you're flying spacecraft at low orbits, essentially, that you can you increase the density of the atmosphere. The atmosphere is going to increase in materials, and so the density goes up. And we're here to talk today about density and drag, and this is real. It happens. So these storms can result in terms of this emission. We normally contact the emission in terms of a solar wind, and this can cause all sorts of changes in plasma in the Earth's magnetosphere. And here's a little cartoon here that shows the Earth is here. Here's a bow shock wave. Essentially, it's coming in from the sun, and this tail is formed around, which because of the Earth's magnetic field. Had we not had a magnetic field, we wouldn't be seeing this, and we wouldn't be here to talk about it. Probably not. So in terms of an energetic activity, the energy from the sun that's being released in this explosion of material has to go somewhere, and it does, and interacts with our magnetic field. In 1859, there was a really huge eruption on the sun. It's been called now the Carrington effect. And the sunspot group, before we had instrumentation, we have eyes, and the astronomer Carrington actually recorded this in his observing log, what this group of sunspots was looking like. And within a 5-minute period, the flare that originated in this region moved from here to here. And unbeknownst to Carrington at the time, this did produce a huge coronal mass ejection. So during this time, this produced, again, strong aurora displays. And again, mind you that the sunspot was aligned with the Earth. I mean, it was looking right at us. So to get the most maximum effects of these coronal mass ejections, everything is in line. Okay, you can get some tangential stuff, but the big ones are going to come straight at and hit you straight away. So they were strong auroral displays that were reported around the world, sparking and fire in multiple telegraph systems. Very interesting. Telegraph operators are getting shocked as a result of the induced voltages in these long wire telegraph systems. So this particular activity was then assumed to have come from this flare that Carrington discovered, or was actually observing. Now, of course, if something like this were to happen today at this scale, we'd have an interesting problem to deal with. In 1859, I guess the worst electrical problems we had with telegraph systems. So now there were similar events that occurred over time, less strong storms, 1921, 1960, but there was widespread radio disruption reported. In 1989, a geomagnetic storm apparently knocked out power across large sections of Quebec. And in 2012, a Carrington-class solar superstorm produced a a large coronal mass ejection, but it missed the Earth. So again, if it came straight in, we'd be talking about that as probably a second huge Carrington effect. Now, the effects on radio reception. You may be familiar with Radio Jove. It's a NASA program, and people can listen to radio outbursts from Jupiter, and also collect with the equipment solar signals that occur when they interact with the radio receiver. And here you see the system that will produce these particular shock fin patterns that can be received. And this was a pattern in February of this year, around the time that we had that huge coronal mass ejection. The sun was really active around that time. The effects of the ionosphere, if you're familiar with the super SID, looking at the effect of sudden ionic disturbances, you can see the effects of a solar interaction with the Earth's ionosphere. And this was from December of last year. And of course, we have old Elon Musk. And of course, some of you may be cheering the fact that we want the sun to really be belting these flares out to keep the satellites at bay. But he had quite a problem. He lost up to 40 of his 49 satellites that were launched on the 4th of February. Now, remember that date because I showed you on the 5th the region where this came from, this large geomagnetic storm. And the satellites, because the Earth's upper atmosphere extended out further than it was and the density increased, typically when they launch satellites, they put them in a low Earth orbit initially just to check everything out before they put them where they're going to ultimately end up. And unfortunately, that altitude was not the place to be that day, when the atmosphere of the Earth, which is hardly anything at that altitude, did increase enough to produce enough drag to cause these satellites to deorbit and burn up in the atmosphere. And this is what they looked like over Puerto Rico when they were coming back. Okay, this is from the spectroheliograph on February 1, 5, and 6. And first of all, I want you to notice these are two halves that are stitched together. And I'm able to do this in much more improved way so you get an entire disk. But you can look at the region here as it moves, as the sun is rotating. And this right here was the time when you had that eruption. Okay, this line is the demarcation between the two halves that was stitched together. So let's take a look at the guts of this thing. It's called the Sol'Ex, and it was designed by Christian Buell in France. And you're able to download all the. By the way, I didn't tell you, but this device is 3D printed. And he'll supply all the STL files, and the program to do all the magic that assembles the images was written by his wife, and all of this is downloadable at no charge. These are the components that are printed, and the only thing you have to watch out for, of course, it's made out of plastic, and you don't want to keep that in the sun too long. But it's a pretty easy build, even for someone like me who's not very good at 3D printing. But the printer was able to do a fine job. And again, I don't know if you've had any experience with 3D printing, you're going to take your file out and ream out things to make sure it's nice and smooth. And depending on how the printer is printing, either going to have extraneous material that you have to get rid of, but it goes pretty smoothly. These are several of the components before it was assembled. This is a blow up of what everything looks like. And this is the guts of this thing. Okay, we have two lenses, We have a slit that's, you can't see here, it's very tiny, and a diffraction grating. So these components can be bought individually or as a kit. Now, to show you the resolution that my system is able to produce, this was an image that I took on the 6th of February with the 25mm aperture. This is an image taken by the SOHO satellite, which has a 40mm aperture. And yes, that's a small aperture for a telescope, but remember, the sun is very bright. So here's a comparison. You can see the sunspot groups here. Okay. So how is an image collected with the Sol'Ex? So this little video loop will explain that from start to finish. And I don't know if the audio is going to come through. If you don't hear audio from this, let me know and I'll just narrate it. Okay, here we go. Do you hear the motor running? Okay, right now, the first step is to find the sun. So the telescope is going to point to the sun. That's what it's doing right now. And you'll see the image of the sun. There it is projected on that little screen. And once that's aligned, then I go ahead and do you hear that? Okay, so what I'm saying is this is the spectroheliograph that's attached now to the telescope, and up here is the 25mm aperture that is collecting the light from the sun. And this white block is essentially just stopping the sun from hitting the spectroheliograph to keep it cool. Okay, and here's the detector here. And this is already dialed in for the H alpha line. And so next we'll go inside and I'll show you the actual process to collect this image from the sun. So here we go now inside the observatory. And what I have set up now is these two screens. One is controlling the program. One is controlling the detector and the telescope. So what I have to do is these controls the scan rate of the telescope. I turned the telescope into a scanning device, much as Hale did, but of course using electronics instead of photographic plates. So the image is going to be in this region. You're going to see when the scan occurs. Okay, this, I guess not, hold on a second. But the programs are here. This is just storing the data as it's collected. Okay, so now we're going to get ready to scan. And what I do is I manually scan this. One technique is you just turn off the drives and let the telescope stay still and let the sun scan through that. But what's going to happen here is I'm going to do that manually. And you're going to see right here, there we go. I've now started the scan. And this dark line is the indicating to me that I'm on the hydrogen alpha line. In other words, I'm tuned to 6,563 angstroms. And so now we have the completion of the scan. And once that's complete, then I'm able to tell the program to go ahead and assemble the 840 or so images that were just recorded in that short period of time. So at this point, I just select, uh-oh, I just killed it. Oh, I don't believe I did that. Let's see if I can, I can't run this fast forward. Oh, well. Okay, that's it. Any questions?
Thank you, David, for an interesting talk. It kind of, one of the things occurred to me while I was listening to you was how really hostile the universe can be sometimes when it produces events like this that can seriously mess up our life here on Earth just in a very casual way. So it's very interesting to hear what you're talking about.
Thank you.
How much for the part for the kit of optics? What kind of money are we talking about?
If you buy the kit from a company in France that puts it all together, it's about 400 euros. If you buy the lenses and the ratings locally, in other words, from companies in the US, it's probably maybe $300. The slit that I used comes from another piece of equipment, another spectroscope that I have. And so I didn't have to buy that. But if you have to buy the slit, that's actually made by the company in France. And you could buy one, but it won't fit properly. You just have to do it. So you could build without the 3D printing for $500 US dollars if you had to buy everything from the company in France.
Thank you. Something to explore.
Did you have a hard time figuring out how to set your imaging levels so that your images came out with the right quality?
Oh, yes. Think of this. I don't know if you remember, there was a Star Trek episode a long time ago where I think it was the pilot one where they landed on a planet and the beings used their minds to create illusions of when they landed. And when Kirk saw, or whoever the captain was in that, when he saw the woman, what she really looked like, because they tried to put her back together, but they didn't have a model. This was what I had with it, because I had no idea how this device was. I mean, I understand spectroscopy, that's what I do, but how all these things would fit together. And you'd be surprised how 3 optical elements could give you a lot of angst. But once I got that done and determined the proper aperture, then the program could control the exposures. I would just go ahead and deal with the exposure until I got what I liked. And I can also, I have a system now where I can actually have the entire disc. Instead of getting a longer slit, which would give me the entire disc, I just used a different telescope with a different focal length. So I was able to bring the entire solar disk onto the detector.
And it looks like you have a pretty fancy tracking system there. So, but you mentioned that it was okay to just let the sun scan across.
Yeah, if you do that,
Mm-hmm.
yeah, that's a problem too, because then you have to deal with the exposure rate. So the exposure that I'm taking is 4.5 milliseconds, and it takes approximately, well, the time that you were watching, it takes approximately several seconds, and I end up with 800 images that are assembled.